This is the video for Lessons 7.4 and 7.5, Part 2, Applying Exponential Growth and Decay. The bad news about this section is it deals with a bunch of word problems, and I know how much you guys love word problems. The good news is that you get to use a calculator. Okay, so any of the things here, we're going to just write out what we would type into the calculator, but from there you would actually use the calculator to do the calculations. Okay, on the test, you will definitely have a calculator to help you. The other good news is that, in my opinion, there's really only one thing you need to memorize, and it is that right there that I highlighted. Okay, that's what we call the exponential growth model. Okay, it looks very similar to what we talked about in the first part of 7.4 and 7.5. So it says A is the initial amount, which makes sense. We said A was that starting value when we dealt with this the first time. Okay, that 1 plus R is what we call the growth factor, but what I really care about is that R is the growth rate. Now the growth rate is usually going to be given to you as a percentage. Hopefully by now we realize that we can't work with percentages in terms of working with different operations, so we are going to need to change that percent to a decimal. And finally, T is the time period. Okay, so let's look at how we are going to use this. Okay, so example 1. The owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. So we're going to write a function that models the value of the car over time. So notice that the other day when we learned just the general form of exponential functions, our x was the exponent. In this case, okay, that t is going to be the exponent. So we're still going to have an unknown exponent in our function, okay, but to make sense in this word problem, it's going to be t. So we're going to say y equals a times 1 plus r to the power of t. That's our exponential growth model, which hopefully you will memorize. Okay, we need to know the initial starting value, which is 11,000. That goes where our a is. We need to know the rate. The rate is 6.9% per year. So just a quick review. Okay, that's the percentage. If we need it to be a decimal, we're going to take that decimal and slide it 2 spots to the left, and we can fill in that 0 there. So 6.9% as a decimal would be 0.069. Okay, and I'm going to plug that in for my r. My t is going to stay, and my y is going to stay. And all I need to do now is I'm just going to simplify this a little bit. So my final function would look like y equals 11,000 times 1.069 to the power of t. Now part B says the auction took place in 2004. What was the approximate value of the car at the time of the auction? Well, it started when the car was bought in 1984, and if the auction took place in 2004, that means it was growing in its value for 20 years. So we're going to take this function we created in part A, plug in 20 for the t, and then we're simply evaluating. So we're going to have 11,000 times 1.069 to the power of 20. Okay, that ideally is on what I want to see on a quiz or a test, because then you would just take your calculator, plug this in, and you should get $41,778. Okay, let's look at example 2. Okay, compound interest. Okay, the good news is when you eventually get a savings account, okay, your bank will kind of pay you for keeping your money with their bank. Okay, unfortunately, it's not a whole lot. Okay, I'm looking at this 4% right now, and that's way too high. But it has to be kind of high, so you'll see what happens here. Honestly, I probably get a couple cents each month for keeping my money in the bank. Okay, so it's not a lot, but at least it's something. It still follows the exponential growth model. So we're going to say y equals a times 1 plus r raised to the power of t. We need an initial starting value. That's going to be the $250 we plugged into the account. Okay, it's 4% interest. 4% would be 0.04. Okay, and in this case, okay, it's not really asking us to write a function. Okay, we totally could write a function because we would just put t there. But if you want to save a little bit of time, Okay, this is just saying how much will our investment be worth in 5 years, so we know that that t is going to be 5. Okay, so we would say 250 times 1.04 raised to the power of 5. We would type that into the calculator, and our answer would be $304.16. Okay, turn the paper over. I want you to try the guided practice and press play when you're ready. Okay, we're going to start with y equals a times 1 plus r to the power of t. Since this one here doesn't ask for a function, I'm just going to plug all my values in and see what I get. So my initial starting value is 150,000. It's going to be 1 plus, the rate is 8%, so 0.08. I want to know what is going to be the value after 5 years. So, my exponent is 5. Okay, if I want to simplify that a little bit, okay, all I would do is add my 1 and my 0.08 on the inside. And if I then type that into the calculator, it would be $220,399.21. Okay, next example is using the general compound interest formula, and this is a crazy looking formula, but if I make you do it, I will definitely tell you what the formula is. Okay, you do not need to memorize this. Okay, however, you do need to know what each part represents. Okay, so our example says you deposit $1,000 in an account that pays 3% annual interest. I'm going to highlight some things. So $1,000, 3% annual interest. Find the balance after 8 years. Okay, if the interest is compounded monthly. Okay, so the other example we did, it was just being added in each year. Okay, however, in this case, okay, it's kind of giving you a little bit more money each month. Okay, so we are using the formula right here. I'm going to rewrite it. So A, the amount, equals P times 1 plus R over N raised to the power of N times T. Okay, and it tells you what some of these things mean. P is the initial amount, called the principal. Okay, so it's still kind of like that amount we're plugging in. Okay, R is still the rate. Okay, the T is still the amount of years, but the N now is how often it is compounded each year. In this case, since it's being compounded monthly, our N is going to be 12. Okay, if it was compounded weekly, our N would be 52, because there's 52 weeks in a year. If it was compounded daily, which would be awesome, okay, it would be 365. Okay, so your T is still the amount of years you're leaving the money in the account for. However, your N is telling you how often it's compounding this interest. Okay, so we're going to plug some numbers in here. Okay, once again, the P is the principal. That's the starting amount, so that's going to be 1,000. 1 plus, our rate is 3%, but we're not going to say 3. We're going to say 0.03. Our N, since it's being compounded monthly, we said that would be 12. Okay, there's another N in the exponent, so it's going to be 12 up there too. And we're leaving it in for 8 years, so 12 times 8. Okay, if you were to simplify this a little bit more, once again, you can definitely do this on the calculator. Okay, this stuff on the inside would give you 1.0025. 12 times 8 is 96. Okay, this is all on the calculator. And if you were to type this in now to get that final value of how much would be in your account, it would be $1,270.87. Okay, so not bad for leaving it in there 8 years. You gained about $271. Okay, so once again, P was the initial starting amount, the principal, R is your rate, T is your time in years, and N was how often it's being compounded each year. Okay, we've got one more example, and it has to do with exponential decay. Okay, and the good thing about exponential decay is it pretty much looks like exponential growth, but notice instead of adding your rate in, you're going to take it away. You're subtracting it. Okay, so we have ponderosa pine forest decreasing from 1963 to 2002 by 0.5% annually. It gives us the starting amount, 41 million acres. Okay, we want to write a function that models the number of acres of ponderosa pine forest in the western United States over time. So our exponential decay model is going to be y equals a, in this case 1 minus r raised to the power of t. So the only thing different is you're subtracting your rate instead of adding it. Okay. Now I know it says 41 million. Okay. Let's just keep it as 41 because in the end we can just say let's apply that million again, and then we don't really have to deal with the huge numbers right now. So our initial amount is 41. Okay, it's decreasing at a rate of 0.5% annually. 0.5%. If I moved it over twice, okay, it'd be 1 minus 0.005. It's going to be raised to the power of t. And if I simplify this stuff right here, it's going to be y equals 41 times 0.995 to the power of t. And that's my function. Okay, now if I want to figure out how much it would be in 2002, okay, well, from 1963 to 2002, we can figure out that that is 39 years. So I'm going to plug that in for my t. So 41 times 0.995 to the power of 39. And if we plug that into the calculator, it'd be 33.7. And all we have to remember that is we were dealing with million, so it would be 33.7 million acres. Okay, so once again, the one thing you need to memorize is what the exponential growth model looks like. The exponential decay is very similar. Okay, you should be able to apply that general compound interest formula, but once again, I will give you that formula to use. Okay, so make sure you write down any questions, and hopefully we can do okay with these word problems you have tomorrow night.